This is Math 251, Section 13.2. We're now going to look at, again, finding double integrals that represent volumes. But this time when we think of our volume, we're going to think of our shape as having a base that's not a rectangle. It's some general region R. So instead of R for rectangle, R is now for region. Notice we still have some surface. Z is equal to f of x and y that forms the top of our three-dimensional shape. And the top is the outline whose shadow is the base, R. We'll do this with a double integral, just like we did before. So our volume is going to be the double integral over this region R of f of x and y dA. But how exactly are we going to define R now that it's no longer a rectangle? In order to set up our limits of integration, we have to take a good look at the shape of our region R. It's important to note that when we write our final double integral, the outermost integral must have constant limits of integration. That's one of the most important parts about setting these things up correctly. In order to determine how to make that happen, I'm going to ask you to think in a lot of the same ways that you thought when you were choosing vertical and horizontal rectangles back in the days when you were finding areas under curves or areas between curves. When I look at this first picture, if the shaded region is just the region R in the xy plane, there's still some surface above it forming the height, but just this region R. Notice that, again, back in thinking about Calc 1 and Calc 2, you would have almost certainly chosen to draw a vertical rectangle to think about finding that area. That vertical rectangle goes from the bottom curve, g of x, to the top curve, h of x. So when I go to write my volume integral, I'm going to say the rectangle itself goes from bottom, g of x, to top, h of x. And notice that those are both y values. They're y equals. So bottom to top, I'm doing dy as my first integral. I then would need to figure out what these ending points are. This intersection point, A, would be the left side, and then just sort of this random vertical line here where we've decided to stop, B, is the right side. So for the dx integral, we'd go from A to B. And notice those are constant values on that outer integral. If you consider the picture at the bottom of the page, this one is going to have to go the other way. If I tried to draw vertical rectangles, I wouldn't be consistent through the whole shape. On the left side, I'd be between the g of x, or g of y curve, rather, two pieces of it, and on the right side, the h of y curve. And I don't want that. I want every rectangle to go from one curve to the other. So instead here, we'd want to draw horizontal rectangles. And to find the volume, I would integrate my height function, f of x and y, from left to right. The left side of this rectangle is on the g of y curve. The right side of this rectangle is on the h of y curve. Those are both x values, x equals, so I'm now doing dx first. And when I go to do dy, I'll notice that from this intersection point to that one, defined my limits of integration for my y values as c to d. Again, constants for those outer limits of integration. Okay. We'll do this with some actual functions in just a moment, but I just want to emphasize one more time that when you are doing vertical rectangles, make sure you're thinking from bottom to top. And when you're doing horizontal rectangles, make sure you're thinking from left to right. in defining your limits of integration. All right, on the next page, if you downloaded my blank notes, you'll have to fill in just a little bit here. The problem says in each of the examples here in example 1, evaluate the double integral over the given region R. I didn't define the function, so if you'd please write that in, y is equal to 4 minus x squared. And then for the first one, we're going to let our region R be what I've now shaded yellow. And you'll have to shade that as well. So, looking at this, I think we're going to be just fine defining vertical rectangles here. And I always like to draw one, just helps me think. Every vertical rectangle goes from the bottom, which is the x-axis, to the top, which is our function 4 minus x squared. And that'll be consistent no matter where I drew it. And my volume, where I guess it's really just my double integral in this case. I'm supposed to be integrating the function xy, so you can think about that function representing the surface or the height. And my vertical rectangle means I'm going from bottom to top. Those are y values, so I'm doing dy first. The bottom is really on the x-axis, or y equals 0. And the top is on the curve, where y is equal to 4 minus x squared. To get the limits of integration for the dx, in this case I can really just look at the picture. Clearly x equals 0 is my left side, and right here at x equal 2, I have the right side. All right, so let's go ahead and evaluate this integral. I am integrating dy first, so x is a constant, and the integral of y would be y squared over 2. And that goes from y equals 0 to y equal 4 minus x squared. Dx waiting its turn out here for later. By the way, just like we've done in the past, if you don't like those extra little constants in here kind of cluttering things up, you can certainly pull them out. So if you'd rather put that as a 1/2 on the outside, that's perfectly okay. All right, fundamental theorem of calculus. I would have x multiplied by, plugging in the y, 4 minus x squared squared. Subtract x times, and plugging in the 0, that one will just give me a 0. Dx, that of course is really nothing, it's just 0. And then I'll finish this up on my calculator. I'll put the whole thing in right at once. I've got 1/2 or 0.5 times the integral of, let's see, 0 to 2, and then my function. And I get 5.3 repeating. Always kind of nice when you can to give an exact answer, so I just changed that to a fraction, and I got 16/3. All right. In the second part of example 1, we have the same function, y is equal to 4 minus x squared, but this time we're using or integrating with our region being a different piece. Our region R now is this piece right from the horizontal line y equals 3 up to the top of the function. I'm going to continue to think about vertical rectangles here. Again, every vertical rectangle would have its bottom or its base at y equal 3 and the top at y equal 4 minus x squared, so they're all consistent. And so to get the volume function, my integrand is still xy. I'm still doing vertical rectangles, so I'll still do dy first, and then dx. This time, the bottom of the rectangle is at y equals 3. And the top of the rectangle is still at 4 minus x squared. And then for the dx, I need to know these intersection points, these x values. You can probably predict them just by looking at the graph, but I'll also remind you that to get those intersection points, you can either graph these two functions, y equals 3 and y equals 4 minus x squared on your calculator, or you can simply set them equal to one another, which is what I'm going to do. That's going to give me x squared equals 1, and x equals plus and minus 1, which certainly seems reasonable when I look at my picture here. So my x limits of integration go from -1 to +1. All right, so let's go ahead and do this integral. Once again, I'm going to get x times y squared over 2. I'm going to pull that over 2, or that 1/2, out front right away, just kind of get it out of my way. And that goes from y equals 3 to y equals 4 minus x squared. Plugging in the 4 minus x squared first, I have x times 4 minus x squared squared. Subtract, plugging in the 3, that'll become a 9x. And once again, we're now down to an integral that, although it's doable by hand, why not take advantage of the technology we have? And I actually did this one kind of offline here. And this one gives you an answer of 0. Now, if you're wondering, or if that's bothering you, don't let it. Think about this. My integrand in this particular case was the function xy. We're thinking of that as our height function, right? But when you think about this region, all of the x's on this side are negative. The x's on that side are positive. And so because of the symmetry, essentially what you're getting is a half negative, half positive. Kind of cancels itself out, and you end up with 0. This is the equivalent, if you think back once again to your Calc 1 days, of having a function that looked like this. The integral here counted as positive, but because it was below the x-axis, the integral there counted as negative, right? And then the complete integral gave us a value of 0 because of the symmetry, the positive and the negative just added together to give 0. What we have here is the three-dimensional analog of that. Half of my shape is going to have a height function below the xy plane. The other half has a height function above the xy plane. This is going to count as a negative contribution towards the volume, and that as a positive one. So, we do get a 0. It's not surprising. If you get negative values for your quote-unquote volumes, don't be shocked. All it means is that they lie below the xy plane. All right, so we will be pausing here, and we'll pick it up in part B.